Hello students, in this video we'll discuss loxodromes or rhumb lines on the unit sphere. Let's consider the sphere under the Mercator projection. Of course, all the Mercator projection means just imagine that the unit sphere is basically just a rectangular strip, right? So there was something that you said a map, okay? And so of course, how do we parameterize that per, we've already seen how we do this over here. So what will it look like? It's gonna be R of U and V is equal to what? Is equal to hyperbolic secant of U cosine of V, hyperbolic secant of U, then the sine of V, then the hyperbolic tangent of U like this. Of course, our standard parameterization of the sphere we know very well, right? Standard parameterization is just R of theta and phi is what? Is cosine of phi, and then a sine of theta, sine of phi, sine of theta, and then cosine of theta over here, right? So with this parameterization, we know that phi constant, so if phi is equal to constant, then those are the meridians. And theta constant are, of course, the parallels. Those are the latitudes, of course, right? So typically we call those the parallels latitudes. All right, and so what do we say? We're going to define, we say that a curve on the sphere is a loxodrome. In old books, they don't call them loxodrome, they call them rhumb lines. That's from aviation theory, right? If the curve makes a constant angle with respect to a meridian, right? So if the curve makes a constant angle with respect to meridians. Of course, the reason that these rhumb lines or these loxodromes are so important is because if you're traveling in an airplane and you want to basically maintain a constant bearing, along with respect to the meridian angle, if you want to keep your plane fixed in one fixed direction, you're going to follow these loxodromes essentially, right? And so in other words, those are the trajectories where the bearing of the plane doesn't change. Of course, if you want to go from point A to point B as quickly as possible, you don't follow a loxodrome, you follow a great circle, right? But nonetheless, they're constant bearing curves on spheres, okay? And so let's figure out what happens for loxodromes. In other words, the question becomes is what do loxodromes look like under this Mercator projection? So that's our question. So question, what are loxodromes under the Mercator projection? Okay. And so how do we figure this out? So what we're going to do is the following. So I need to say that what is the, what do we know? So let gamma be a loxodrome. So let gamma be a loxodrome. Okay. Now, what's gamma dot going to be? So of course, gamma depends on U and V over here, right? So in other words, what will gamma dot be? So gamma dot, the derivative of gamma, is going to be what? It's going to be negative hyperbolic secant of U, hyperbolic tangent of U, cosine of V U dot, like that, plus what? But then of course minus, because it's going to be sine, right? Negative sine. So negative sine, negative hyperbolic secant of U, then sine of V, V dot, comma what? Comma, and then same thing over here. So negative hyperbolic secant of U, hyperbolic tangent of U, times the sine of V U dot, and then plus hyperbolic secant of U, and then cosine of V, and then a V dot. Finally, hyperbolic secant squared of U dot, like that. So in other words, that's the derivative That's the velocity vector or the tangent vector of this curve over here. And now, of course, what's a tangent to the meridian, right? So in other words, we know that a tangent to the meridian, so tangent to meridian is just going to be RU relative to the length of RU. That's the unit tangent vector of the meridian, okay? Now, of course, we know that that's going to be, so let's do R sub U, right? So what's this going to be over here? So I know that the length of RU, so RU dot RU is going to be the first fundamental formula. That's going to be secant squared. So that's just going to be a hyperbolic secant, right? So I'm going to multiply this by hyperbolic cosine of U. And then what will RU be? So in other words, RU is going to be the same thing over here. It's going to be just negative hyperbolic secant of U, hyperbolic tangent of U, and then what? And then a cosine of V. And then over here, we're going to have the same thing, negative hyperbolic secant, hyperbolic sine. These are all secants, right? So yeah, that's not hyperbolic sine, that's hyperbolic secant. Force of habit, hyperbolic secant of U, then hyperbolic secant of U, hyperbolic tangent of U, times the sine of U, right? Sine of V. And then finally, hyperbolic secant squared of U, like that. Good. All right, so that's my U over here, right? And I know that this has to be a constant, right? So in other words, gamma dot product, the inner product of this with RU, in other words, either the angle between these two things, in other words, that's a tangent to the meridian, that's a tangent to the curve. I know that they have to be constants. In other words, this has to be equal to the cosine of some angle over here between them. Let's call the angle over there, what haven't I used yet? Cosine of, let's say, just alpha, like that, okay? And so what does that tell me? So let's do these dot products over here. So when we do the dot products, what's going to happen? So we do this over here, and then this over here, we're going to have a positive hyperbolic secant squared, hyperbolic tangent squared, and then U dot times cosine squared. And if I do this over here and this over here, I'll get a hyperbolic secant squared, hyperbolic tangent squared, sine squared V, U dot, right? And so those will give me 2 U dots, so then that would be hyperbolic. So in other words, all these things together are going to give me what this implies. This is going to be equal to, well, let's do it slowly over here. So I'll have a hyperbolic secant squared, hyperbolic tangent squared, cosine squared, hyperbolic secant squared of U, hyperbolic tangent squared of U, times the quantity what? Times cosine squared for this one, cosine squared of V plus sine squared of V. Those are the what? Those terms over there are going to give me a U dot, like that. And all this is multiplied, of course, by hyperbolic cos, where I'm doing at the very end, right? Now, when I do these V dot terms over here, I'm going to have this term over here, right? And then that's going to be hitting with this. So that's going to give me a positive hyperbolic secant squared, tangent squared, sine, cosine. Over here, when we do this second term over here, dot this, we're going to have positive, and then this term over here, dot this term over here, we're going to have a negative hyperbolic squared, tangent squared, sine, cosine, V dot. So there's no V dot term over there. And then finally, we're going to have a what? We're going to have plus hyperbolic secant squared, to the fourth, of course, U, like that. And all this is hit with what? All this is going to be hit with cosh, right? Cosh of U, like that, right? Now, of course, that's equal to 1 over here. So it's going to be a U dot. So it's going to be a U dot, and then a what? And then if I pull out a hyperbolic secant squared, then I'm going to have a 1 over here. So that's going to be hyperbolic secant squared. So that's going to be hit with 1 hyperbolic cosh. So all this is going to turn to a hyperbolic secant squared. Hit with 1 cosh is going to give me a hyperbolic secant squared of U, like this. Now, what's that going to force? I know that since this is going to be a, it's an unit speed parameterization, I know that U dot squared, U dot squared, so that's what the cosine of theta is equal to, right? So in other words, what's U dot? So if I solve this equation for U dot, that tells me that U dot, one final step over here, so U dot hyperbolic secant squared is equal to cosine of theta. So that tells me that U dot is equal to the cosh of U times the cosine of alpha, right? Now we know that V dot squared plus U dot squared times what? Times the length, of course, hyperbolic secant squared of U has to be equal to 1. That's my unit speed parameterization assumption, right? This is my unit speed parameterization assumption of the Loxodrome. Great. Okay. And so now, of course, what's going to happen over here? So let's fill in, was this something about v dot over here? This is going to say that v dot squared plus what? Plus cosh squared u cosine squared alpha times hyperbolic secant squared u is equal to 1. Of course, those are going to cancel out over here. So what's that going to tell me? That's going to tell me that v dot squared is going to be equal to what? V dot squared times hyperbolic secant is going to be equal to what? That's going to be just a 1 minus cosine squared. 1 minus cosine squared is going to be a sine squared. So sine squared of alpha. And therefore, v is going to be what? Therefore, v dot, so v dot is going to be what? Is going to be plus minus sine of alpha times cosh of u. Cosh of u, like that. Beautiful. So now I have an equation for u dot. I have an equation for v dot over here, right? And so now I can look at dv du. So what's dv du going to be? So dv du is going to be what? It's going to be v dot over u dot, right, by the chain rule. And so that's going to be what? That's going to be plus minus sine over cosine. That gives me a tangent of alpha, and then cosh u over cosh u, there's nothing there, right? So in other words, there's no dependence. In other words, the derivative of v with respect to u is a constant, so that says that v is going to be plus minus the tangent of alpha times u plus another constant, let's call it c1 over here, in other words. So what are these graphs over here? So in the UV plane, those are just straight lines that make an angle of alpha, right? So these equations over here are all just straight lines. That's a straight line. Okay. So what have we just shown? So in other words, under the Mercator projection, what are the Loxodromes? The Loxodromes over here are going to be straight lines. Okay. So if you look at a Loxodrome on the sphere, the Loxodrome is going to be sort of moving around constant angle with respect to the meridian, right? So the Loxodrome is going to do something like this and start to spiral a little tighter to get to the top of the sphere, the north or the south pole, right? So the Loxodrome is going to move around the curve, right? When you project that Loxodrome by the Mercator projection onto the strip, what's going to happen is that Loxodrome is going to turn into a straight line. If I can foliate the plane over there, the strip with all these straight lines, and all those Loxodromes will be by through the inversion under this Mercator projection. Thank you very much.